Welcome. We are discussing our fourth chapter. The central theme of this chapter is line integrals. Today, we are going to discuss the second module of this chapter. In this module, we shall discuss curves and their arc lengths. We start this module by recalling the definition of a curve. Curve. By a curve in Rn, we mean a continuous map, say gamma, from I to Rn, where I is an interval. We repeat that by an interval, we mean a connected set in R. Since the continuous image of a connected set is connected, it follows that the range gamma I is a connected set in Rn. Thus, we can say that a curve is a vector valued function of a single real variable, with a restriction that the domain should be connected. One remark at this point: unless otherwise stated, we usually do not consider the case that gamma is a constant map. We know that a constant map is continuous, because in this case the range gamma I reduces to a singleton set in Rn. We now define trace of a curve. By the trace of a curve gamma, which is a map from I to Rn, we mean the collection of points gamma I, that is the range, that is the collection of points gamma t, where t varies over I and obviously it is a subset of Rn. It is to be noted that different curves can cover the same trace in different ways. We have already shown it with the help of some examples in an earlier module. One example: for every natural number m, we define gamma m from the bounded closed interval 0, 1 to Rn by gamma m equals the n tuple t to the power m, the rest are all zeros. Then one can easily check that this collection of infinitely many curves have the same trace, that is, the line segment in Rn joining the points the origin and 1, 0, 0, 0, 0, 0. The purpose of this module is to introduce the concept of arc length of curves. In the study of line integrals, the actual manner in which the trace is covered by a given curve is more important than the trace of the curve. And we are going to introduce line integrals in the next module. So, we need another definition: graph of a curve. Let gamma from I to Rn be a curve. By the graph of gamma, we mean the collection of points graph of gamma defined by collection of elements where the first comes t, then n tuples which represents gamma t, where t varies over I. Clearly, graph of gamma is a subset of Rn plus 1. Clearly, different curves has different graphs. We now recall the concepts of velocity and speed of a curve. Let gamma from I to Rn be a curve. Also let gamma 1, gamma 2 up to gamma n be the components of this curve gamma. By the velocity of gamma at a point t in I, we mean the vector which is given by the n tuple gamma 1 dash t, gamma 2 dash t up to gamma n dash t, provided all these derivatives exist. The norm of velocity vector of a curve is called its speed. By the speed of the curve gamma at some point t in I, thus we mean the scalar norm gamma dash t, provided it exists, that is, gamma dash exists at the point t. Smooth curve. Let gamma from I to Rn be a curve. It at every point of the interior I, the velocity vector gamma dash t exists and is continuous, then gamma is said to be a smooth curve. Next, we introduce another concept, piecewise smooth curve. Let gamma from I to Rn be a curve. If the interval I can be partitioned into a finite number of subintervals such that the restriction of gamma is a smooth curve in every such subinterval, then it is said to be a piecewise smooth curve. Clearly, any smooth curve can be considered as a piecewise smooth curve. For the forthcoming discussions, we need to know arc length function of a piecewise smooth curve. If any part of a given curve is linear, then we can easily measure the length of the linear part, that is its arc length. In case it is not so, we can say that the arc length, say L, between any two points of the curve is strictly greater than the length of this chord. Say the length of the chord is C and the chord joins these 2 points. Now, if we consider a third point between those 2 points considered earlier, and if C dash be the sum of the lengths of these 2 chords formed, then we have C strictly less than C dash, which is strictly less than L. Now, if we go on inserting such immediate points on the curve, then the sum of the lengths of such chords, that is the length of inscribed polygon, will always be less than the arc length of the curve. But inserting more such points will make the difference less. Thus, it is meaningful to define the arc length of a curve as the least upper bound of all such inscribed polygons, provided it exists. The formal definition follows. Arc length of a curve. Let gamma from a bounded closed interval AB to Rn be a curve. If there exists a positive real capital M such that corresponding to any partition P given by A equal to T0 less than T1 less than continuing up to Tm equal to B of the interval AB, we have summation from k equal to 1 to m of norm of gamma tk minus 1 lesser equal to m, then gamma is said to be rectifiable. The above sum is called the length of the polygon induced by the partition P. This implies that the length of all possible inscribed polygons is bounded above. In case we find no such m, then the curve gamma is said to be non-rectifiable. One can easily understand that this classification, whether a curve is rectifiable or not, among all curves with compact domain is exhaustive. That is, every curve is either rectifiable or not. We cite two examples here. First example, for a rectifiable one, we consider the curve gamma from bounded closed interval 0 to 2 pi to R2 given by gamma t equal to ordered pair cosine t sin t for every t belonging to 0 to pi. Clearly, this is nothing but the unit circle, and we can easily check that it is a smooth curve. We consider any partition P equal to 0, which is T naught, strictly less than T1, continuing up to Tm, which is 2 pi of the interval 0 to 2 pi. We check norm of gamma tk minus 1 equals with norm of gamma dash xi k multiplied by tk minus 1 using mean value theorem. Here xi k is some point intermediate between tk minus 1 and tk. So, we can write this as norm of gamma dash xi k into modulus tk minus 1. So, this equals with norm of the vector minus sin xi k cosine xi k multiplied by tk minus 1. Since the elements t0, t1 is increasing, tk minus 1 is positive. So, this is lesser or equal to 1 times tk minus 1. This implies summation from k equal to 1 to m of norm gamma tk minus 1 lesser or equal to summation k equal to 1 to m 1 tk minus 1, that is nothing but 2 pi. This shows the curve gamma is rectifiable. Now one example showing a non-rectifiable curve. Let gamma from open 0 to closed 1 to R2 be a curve defined by gamma t equal to ordered pair 0 sine 1 upon t for every t belonging to semi-open, semi-closed interval with left endpoint 0 and right endpoint 1, which is closed at the right side. Our intuition tells us that the second coordinate sine 1 by t may create problem on rectifiability. So let us concentrate on this. We consider a sequence Tn defined as follows. For every natural number n, Tn is defined by the reciprocals of pi times n plus half. It is easy to find that the sequence Tn is monotone decreasing and also it converges to 0. Then for every natural number n, sine of 1 upon Tn equals sine pi times n plus half. So this equals to minus 1 to the power n. Now we consider any interval closed, bounded with left endpoint Tn and right endpoint T1 and its partition P equal to Tn, Tn minus 1 continuing up to T1. Then the variation of the function sine 1 upon Tn over the interval is given by summation k equal to 1 to n minus 1 modulus of sine 1 upon tk plus 1 minus sine 1 upon tk, which equals with twice n minus 1. And clearly this quantity is not bounded. So the total variation of one component of the given curve over any open interval with 0 as the left endpoint is unbounded. We consider the other component 0. As a result, the curve under consideration is not rectifiable. Now a natural question is, if some curve is rectifiable, how to measure its arc length? We are trying to give an answer to this question. The following result gives us a relation between the arc length function of a piecewise smooth curve and its velocity. Result: let gamma from bounded closed interval AB to Rn be a curve. If the velocity function gamma dash is continuous on this interval AB, then the curve is rectifiable. Now let its length be denoted by LAB. Then LAB satisfies the inequality LAB less or equal to integral from A to B norm gamma dash t dt. Later we shall show that actually LAB will be equal to this integral. Now we prove the result. Let P given by A equal to T0 less than T1 continued up to less than Tm equal to B be any partition of the interval AB. Then the length of the inscribed polygon equals summation k equal to 1 to m norm gamma tk minus gamma tk minus 1 which equals with summation k equal to 1 to m norm of integral tk minus 1 to tk gamma dash t dt. That is summation k equal to 1 to m norm of gamma tk minus 1 equals summation k equal to 1 to m integral tk minus 1 to tk norm of gamma dash t dt, which equals with integral a to b norm of gamma dash t dt. In case the curve is piecewise smooth, the above result is true for every part of the curve for which it is smooth. We add the corresponding inequalities and get a similar result. Thus, we find that the number integral a to b norm of gamma dash t dt is an upper bound of the lengths of all inscribed polygons. As a result, the curve is rectifiable and we have LAB less or equal to integral a to b norm of gamma dash t dt. Note: this means that the length of a rectifiable curve can never be greater than the integral of its speed. After a few steps, we shall show that actually they are equal. Now we shall prove the additivity of arc length function. The result reads like this. Let gamma from AB to Rn be a rectifiable curve with arc length LAB. Now let A less than C less than B, and we define two curves, gamma 1 and gamma 2, defined as follows. Gamma 1 from AC to Rn and gamma 2 from CB to Rn be defined by gamma 1t equal to gamma t for all t belonging to AC, and gamma 2t equal to gamma t for every t belonging to C to B. That is, we consider gamma 1 as the first part of gamma and gamma 2 as the remaining part of gamma. Then gamma 1 and gamma 2 are also rectifiable curves. Moreover, if LAC and LCB denote their lengths respectively, then LAB equals with the sum of LAC and LCB. We give the proof. First, we assume that P1 and P2 are arbitrary partitions of the bounded closed intervals AC and CB respectively. Clearly, P equal to P1 union P2 is a partition for AB. We consider the two polygons inscribed in the curves gamma 1 and gamma 2 induced by the partitions P1 and P2 respectively. Let their lengths be denoted by psi P1 and psi P2 respectively. Now their join is a polygon inscribed in the curve gamma. So, sum of the lengths of polygons inscribed in the parts gamma 1 and gamma 2 equals with the length of their join. That is, psi p is given by the sum of psi p1 plus psi p2. Now, by proposition, gamma is rectifiable. So, this sum psi p is always bounded above by LAB. As a result, psi p1 must be lesser or equal to LAB as well as psi p2 lesser or equal to LAB. As psi p1 and psi p2 are bounded above, so the curves gamma 1 and gamma 2 are rectifiable. Let LAC and LCB be the lengths of the curves gamma 1 and gamma 2 respectively. Now we find that 0 lesser or equal to psi p1 plus psi p2, which equals with psi p but lesser or equal to LAB. This implies that 0 lesser or equal to psi p1, which is lesser or equal to LAB minus psi p2. Now we keep the partition P2 unaltered and at the same time allow P1 to be any arbitrary partition of AC. From the above relation, we have 0 lesser or equal to psi P1 lesser or equal to LAB minus psi P2. Hence, we have 0 lesser or equal to supremum of psi P1 lesser or equal to LAB minus psi P2, as the above step was true for every partition P1. Thus, we have 0 lesser or equal to LAC lesser or equal to LAB minus psi P2. Now, it is time to allow P2 to be any partition of CB. Then from the above relation, we have 0 lesser or equal to LAC lesser or equal to LAB minus psi P2. This gives 0 lesser or equal to psi P2 lesser or equal to LAB minus LAC. So, 0 lesser or equal to supremum of psi P2 lesser or equal to LAB minus LAC, as the above statement was true for every partition P2. This gives LBC lesser or equal to LAB minus LAC. That is, LCB plus LAC lesser or equal to LAB. On the other hand, let P be any partition of AB. We consider the partition P union singleton C. Clearly, this is an refinement of P. Now, we can express P union singleton C equals P1 union P2, where P1 and P2 are partitions for AC and CB respectively. Consequently, for the lengths of inscribed polygons, we have 0 lesser or equal to psi p lesser or equal to psi of P union singleton C equals psi of P1 union P2 equals psi p1 plus psi p2 lesser equal to LLC plus LCB. This indicates that the collection of all possible SPs is bounded above. So, considering their supremum, we have LAB lesser equal to LAC plus LCB. Combining the derived inequalities, we have the desired result. This property is called additivity of the arc length of rectifiable curves. Now, the arc length function of a rectifiable curve. Let gamma from AB to Rn be a rectifiable curve. Then any part of gamma is also rectifiable. We define a function S from bounded closed interval AB to R as follows. For every t in open A closed B, St equals LAT, which equals with supremum of the length of all polygons inscribed in the portion of gamma with endpoints gamma A and gamma T, and SA is defined to be the 0. One result here, the arc length function of a rectifiable curve is strictly increasing. The proof. Let gamma from bounded closed interval AB to Rn be a rectifiable curve, and we select 2 points T1, T2 from AB with T1 less than T2. Let us also consider T1 is greater than A. To prove the proposition, we are to show that ST1 less than ST2. We find ST2 minus ST1 equals LAT2 minus LAT1, which equals with LT1 T2 by the previous result. Now, LT1 T2 is greater than equal to norm of gamma T2 minus gamma T1. This is the length of the chord and it must be greater equal to 0. So, now it remains to prove the strict inequality. If gamma T2 and gamma T1 are distinct points, then it follows from the defining properties of norm. If gamma T2 and gamma T1 denote the same point in Rn, that is at this point the curve gamma cross itself, then we assume that gamma is not the constant function in the open interval T1, T2. So, we can always find a point T3 in open interval T1, T2, which is a subset of AB, such that gamma T3 is different from gamma T1, that is gamma T2. Then L of T1, T2 is greater than equal to sum of norm gamma T2 minus gamma T3 plus norm gamma T3 minus gamma T1, which is strictly greater than 0. This completes the proof. One remark here. In order to avoid the above complicated situation, some books further assume that gamma dash t not equal to 0 for every t from the bounded closed interval AB. Even in some books, this condition is a part of the definition of rectifiability. Before entering into the next topic, let us recall the first fundamental theorem of calculus. Let f from bounded closed interval AB to R be a function such that for all x in AB, integral a to x fu du finitely exists. Let C be a member of the closed interval AB, and another function capital F from AB to R be defined by fx equals integral c to x fu du for every x in AB. If the function small f is continuous over AB, then the function capital F is differentiable over the corresponding open interval AB. Moreover, the relation between these two functions is given by capital F dash x equals fx for every x in open interval AB. Result. Let gamma from bounded closed interval AB to Rn be a rectifiable curve with arc length function S from AB to R. Let norm gamma dash denote the speed of the curve gamma. If gamma dash is continuous on closed interval AB, then we have first S is differentiable in AB, Secondly, for every t in open interval AB, S dash t is nothing but norm of gamma dash t. We shall prove this result, but before that, we notice that if this result is true, then our earlier proposition is also true. We proved the inequality, so it will be now equal. Proof. Let us define a function f from bounded closed interval ab to r by ft equals integral a to t norm of gamma dash u du. Using first fundamental theorem of calculus, we claim that f is differentiable and f dash t equal to norm of gamma dash t for every t from bounded closed interval ab. Thus, it remains to show that for all suitable t, S dash t equal to norm of gamma dash t equal to f dash t. Let t belonging to the open interval AB. We select non-zero h such that t plus h is also a member of the open interval AB. Now we consider the difference quotient norm gamma t plus h minus gamma t by h, which is norm of gamma t plus h minus gamma t minus mod h. First, let h be positive. Then norm of gamma t plus h minus gamma t less or equal to L t t plus h, which equals with S of t plus h minus st. This implies norm of gamma t plus h minus gamma t by h less or equal to S of t plus h minus st by h, as h is positive. This is less or equal to 1 by h integral t to t plus h norm gamma dash u du. So, this equals 1 by h integral a to t plus h norm gamma dash u du minus integral a to t norm gamma dash u du, which equals with 1 by h f of t plus h minus f t. In case h is negative, we can find the same result using similar steps. Letting h tending to 0, we find limit of norm gamma t plus h minus gamma t by h as h approaches 0 less or equal to limit h tending to 0 s of t plus h minus st by h. This less or equal to limit h tending to 0 f of t plus h minus ft by h. That is norm of gamma dash t less or equal to s dash t less or equal to f dash t. Since we assumed f dash t equals with norm of gamma dash t, it follows that s dash t equal to norm of gamma dash t. This completes the proof. Thus, we can measure the arc length of any rectifiable curve provided we know the speed of that curve. Now, we shall discuss the concept of reparameterization of a curve. This concept is mostly used in the study of differential geometry. First, we say what do we mean by reparameterization of a curve. Then we shall show that the arc length function of a rectifiable curve is unaltered under reparameterization. Reparameterization of a curve. Let gamma from I to Rn be a curve and f is a map from J to I, which is continuous surjective, and J is an interval. Then the map beta equals to gamma composition f from J to Rn is another curve. It is called the reparameterization of gamma. We usually desire that the function f should be bijective so that the trace of gamma is traversed exactly once by beta. For this reason, unless otherwise stated, in the following discussions, we shall consider that the change of parameter function, that is f, should be differentiable with non-vanishing derivative. In case f dash greater than 0, the reparameterization is said to be orientation preserving, because in this case gamma and beta traverse their common trace in the same direction. In case f dash less than 0, the reparameterization is said to be orientation reversing. In this case, gamma and beta traverse their common trace in the opposite direction. To be very precise, we want our change of parameter function f to be a diffeomorphism. Our first result, arc length of a rectifiable curve remains invariant under reparameterization. Now we give the proof. Let gamma from I to Rn be a curve and f from j to y be a continuous surjective map where I and j are intervals. Then beta equal to gamma compose f from j to Rn is a reparameterization of gamma. We further assume that f is differentiable with f dash s non-zero for every s in j. Let CD are members in j with c less than d and fc equal to a, fd equal to b. Clearly, a and b are distinct as f is 1, 1. Let t equal to fs. So, beta s equals gamma composition fs, that is gamma of fs, that is gamma t. First we assume f dash is greater than 0 for every s. Then integral c to d norm beta dash s ds equals with integral from fc to fd norm gamma compose f dash s ds dt dt. That is integral c to d norm of beta dash s ds equals with integral a to b norm gamma dash fs f dash s ds dt dt. This equals with integral a to b norm of gamma dash fs modulus dt ds ds dt dt. Here f dash s, that is dt ds, is positive. So we have this equals with integral a to b norm gamma dash t dt. In case ds dt is less than 0, the reparameterization is orientation reversing. So the limits of the integration will change. The change in of sign due to this will take care of the other negative sign which evolves when we extract the modular sign. This completes the proof. Now another result. Any smooth curve admits a unit speed reparameterization. Let gamma from I to Rn be a smooth curve. We fix some a which is an interior point of the interval I and define a function s as follows. S equal to st defined by integral a to t norm of gamma dash u du. Then the derivative ds dt at t exists with ds dt at the point t equals with norm of gamma dash t. By proposition, gamma is smooth. So, ds dt greater than 0. By inverse function theorem, S admits an inverse function t equal to Ts, which also satisfies dt dss equals with reciprocal of ds dt at the point t. So, dt ds greater than 0. Let beta denote the reparameterization of gamma defined by beta s equal to gamma of Ts. One can easily check that norm of beta dash is 1, that is beta is a unit speed curve. So, in this module we discussed smooth curves, piecewise smooth curves, rectifiable and non-rectifiable curves and properties of rectifiability. We conclude here.